much. It gives us great pleasure to introduce Lars. So big round of applause. And I'm over to Lars.
Thank you. Okay, thank you very much. So I want to talk about probability monads on steroids today. So first I will quickly recap what normal probability monads are. And I like them very much. So in the life of every Haskell developer, there is the before understanding monads and the after understanding monads. And for me, that example was the one that finally made it click and made me understand monads. And so I work for HaskellX, so we do blockchain technology. And so obviously we worry about distributed systems. And so this work came out of that we wanted to understand our peer-to-peer networks, how long it takes for packages to get from A to B, basically. So that's what this was inspired by. So I try to first recapitulate probability monads and then show how one can think about adding time and concurrency to those. And as a leading example, we have a network like that with 4 nodes. And some of the nodes are connected, so they can talk to each other directly. In this case, it's unidirectional, so 1 can contact 2, and 2 can contact 4, and 1 to 3, and 3 to 4. And let's just assume that all these edges have the same properties. In this case, that a signal takes between 1 and 2 seconds uniformly distributed to hop along one of those edges. And it can even fail. So there can be some network error. So with a probability of 10%, it can fail. And the question is, if you have such a network and the signal starts at 1, will it reach 4? And with which probability, and how long will it take? And this graph is relatively easy still. It gets much more complicated when we add that additional edge. So same questions for that one. So in this talk, I try to come up with a monad in Haskell that can actually answer that question. Right, but first to traditional probability monads. So first we need a concept of probability. I could, of course, simply use rational or double, but I want to make that a bit polymorphic. So prop P, you can just think of double. And now there are, of course, several ways how one can introduce an abstract monad in Haskell, for example, with free monads or with type classes. So in this talk, I want to use the type class approach. So what is a monad prop for monad probability for me? So it has this one method, coin. And coin just means I'm flipping a coin, and with probability P, I get true, and with probability 1 minus P, I get false. And often, instead of coin, it's more convenient to have pick, so you can just pick a random element from a non-empty list, uniform probability, so each element has the same probability of being picked. And for efficiency reasons, you probably, in practice, would want to implement that separately from coin, but you can, I mean, coin is more primitive, so once you have coin, you can actually implement pick by just looking at the length of the list and then picking the first element with probability 1 over length. And if you pick it, you pick it. If not, you recurse on the tail. And so obviously, if the list is empty, you couldn't do it. Therefore, I use this non-empty list type. But in practice, for convenience, I also define this unsafe pick, which if you know what you're doing and you know your list is not empty, you can just use a plain old list. OK, and with that, as simple as it is, we can already do lots of fun stuff. So for example, we can throw a die. So a die would just use this pick from the list 1 to 6, the non-empty list 1 to 6. And then, of course, you can use normal applicative syntax and monad syntax. Once you have one die, you can have n dice by just replicating the throwing of 1 n times and summing up the results. Yes? That's from non-empty lists. So non-empty list, that's the constructor of non-empty lists. It takes one element, the head, and then an ordinary list as the tail. And that's the constructor of non-empty list. So this is the non-empty list that has 1 at the head and then 2, 3, 4, 5, 6 at the tail. It's like the colon, the cons in the normal list. except it doesn't have the nil constructor. Right. So that's just pedantic. You could just use normal list, but then if it's empty, it would crash. Right, and this is actually my favorite example in the whole world. I don't know whether everybody is familiar with this Monty Hall problem. So it's this game show where you can win a car or a goat if you're out of luck. And actually, the program here explains how it works. So there are 3 doors. Again, this non-empty list constructor, so door 0, 1, 2. And randomly, the car is behind one of those doors. So the prices are just behind the car door, there's a car, and behind the other 2 doors, there are goats. Then the candidate can pick one of those doors, so that's his guess. And then the Monty Hall, he opens one of the 3 doors. He doesn't open the one that was picked, and he does open one where there's a goat behind. So there's always at least one door with a goat behind that wasn't picked. So he opens that. So now the candidate has picked one, and the Monty Hall opens another one with a goat behind. So this is now in this stage. And then the interesting part is now the candidate has the choice to either stick with his original guess or switch. So this is these 2 strategies. So he can stay or change. So if he stays, he just ignores this open door information and sticks with his original guess. If he changes, then he picks the 3rd door that he didn't guess before and that isn't opened. And then he gets his price accordingly. And the question is, should he stay or should he change? And it seems there have been like flame wars about that. And so now we have this program, but of course we can't run it because for now this is just a type class, so we don't have an implementation yet. And easy implementation with these sorts of things is always, let me just close that silly window. An easy implementation of these things is always sampling, where you don't get exact results, you just use random numbers. So if you have a monad random, that just means it's a monad where you can have access to randomness. Then you can sample from this probability monad. So I just use a new type wrapper around monad with randomness, and it's very simple. So I use the randomness in the monad to draw double between 0 and 1. And then if that drawn double is less than my probability, then I return true, otherwise false. So that's very easy implementation of this monad prop. And then we can try that for the dice, for example. So we can throw 40 dice with this implementation just in I/O for simplicity. Of course, we could also use a monad random that has deterministic randomness with a given seed. And in this example, so 40 times I got that. And we can also apply it to the Monty Hall problem. And 15 times, and I mean, because the word car is shorter than the word goat, we can see that it seems to be better to change. But of course, that's no proof. And I mean, I could repeat it. I could do it more than 15 times. But of course, it would be much nicer if we got just the exact result. And if we only wanted to use randomness, then of course, it would be pointless. We could just forget about monad prop and just use monad random. So give a second implementation where you actually get exact distributions out of such a computation. And there are various ways how one can do that, more or less sophisticated, using continuations, free monads, whatever. But this is very simple. It's not very performant probably, but I think it gets the idea across. And for small examples, it works beautifully. So the idea is to simply use lists of pairs where each such pair A, P represents result A with probability P. And there is the additional condition that all the P's sum up to 1. So because I will get 1A. And of course, morally, what we really want is a distribution. So we would like a map from A to P. But for technical reasons in Haskell, we can't do that because it must work for all A, and map is only defined for, or only works for A's with an odd instance, so we can't directly use that. Right, and then we have to implement our monad prop. So that's simple. So applicative is just boilerplate. Return is just we have with probability 1 that one value, so there's no randomness involved. Bind, so we get an A with probability P, then we apply the continuation to that A. We get a B with probability Q, so the final result is B, and the total probability is P times Q, because first the A came with probability P, and then the B with probability Q. And this all happens in the list monad, so this is, of course, iterates over all elements of the first list and all elements of the second list and combines them. Okay, yes?
The events are independent, I guess, if you're using the product. You've got two events, and then you can multiply elements.
Well, but no, I mean, it's first A and dependent on A, then the B. But I mean, the A happens in P% of all cases, and then in those P%, in Q% of all cases, the B happens, so it's P times Q. Right, of course, the most interesting part is how I implement the coin flipping, and that's very simple. It's just this two-element list, so it has true with probability P and false with 1 minus B, so basically just the definition. And then this prop L odd is just a convenience function, so if the A happens to have an odd instance, I can indeed just transform it into a map, which just means that I get rid of duplicates and combine them. And then we can now get our exact results. So for the two dice, we get what we expect, that 2 and 12. Oh, and in this case, now I use rational probability, so it's really exact, no rounding errors. So we get what we expect. With 1 over 36, we have a 2 and a 12, and the 7 is much more probable, it's 1 over 6. And now, of course, what we've all been waiting for the Monty Hall. We see that staying is stupid, because then you get the car in 1 of 3 cases, whereas if you change, you get it in 2 of 3 cases. So that should hopefully settle that discussion once and for all. Okay, so I think that's very nice, but now, of course, if we think about the original motivation, we want to use, somehow get time into that. So, and so the first thing we want to do is we want to have a concept of delay. And so I want to keep it simple, so delays, just discrete delays. So first I introduce time. That's just, you can again think of double or rational. And so now I extend my monad prop to a monad delay, and that just has one additional method which delays by a given time. And oh yeah, and I also use a monad error constraint, because I also want that things can go wrong. So the delay is basically infinite, and it just doesn't give a result. And so this is in that context normally called absurd. So absurd is just implemented by throwing an error. I don't care about error messages, so the type of error messages is just unit. And catch is not important. It's just because in this case, I mean, normally catch takes this handler that takes an argument, but in this case it's unit, so we can write that a bit simpler, but it's not needed for this talk. And in practice, of course, we don't just have delays. Like in my original example, I said I'm interested in this 1 to 2 seconds uniformly distributed. So, but this I can now express at least approximately. So the idea is if I want a uniform distribution between 1 and 2, I just split the interval between 1 and 2 into 10 pieces or 20 pieces and pick each of the delays in between with equal probability. So this I can now implement with what I already have. So this is just edge cases so I want a uniform distribution between delay A and B. So if the B is smaller than A, this can't happen, and if it's equal, it's just an exact delay. So this is the normal case where it's a proper interval. And then I just take the width of the interval, divide by the number of pieces I want, and use my pick to pick one time in that interval and delay by that time. And then that's already relatively pretty what we can do with that. So, oh yeah, and in practice, one could also, instead of just using discrete delays, one could use more complicated distributions, like put the uniform, allow uniform delays. And but then implementing the stuff that's going to come would be more complicated. So I stick with this. Okay, and then, for example, uniform delay between 1 and 2 with 20 subdivisions looks like this. Not very exciting, but you see all delays between 1 and 2 are equally probable. And things already become more interesting if you do 2 of those in sequence. So if you wait uniformly 1 to 2 seconds and then again, it looks like this. So what's that? Yeah, 3 seconds is the most probable, and the extremes are 2 and 4 seconds. It's similar to the 2 dice, of course. And it gets prettier and prettier the more you do. So if I do 3 in a row, then it looks like this. And of course, I mean, if for the mathematicians in the audience, the central limit theorem tells us if I do more and more, then it looks more and more than a Gaussian eventually. So even though it's just a discrete approximation, we can see that we at least get an idea of the continuous, what will happen. So that's good, but of course for this network example that I want to tackle, that's not enough, because what I have now is I have probability, so coin flipping, and I have delay that I can compose in sequence. But in these networks, things don't happen in sequence, they happen in parallel. So I need some additional thing to have computations in parallel. And but before I get to that, I haven't told you how to implement this and this monad delay. And that is actually quite simple and can be done with standard monad transformers, because this delay is just a write. So I simply, maybe I should use that as well. So I simply put on an except t monad transformer to get my monad error instance. And then I tuck on a writer t to get my delays. And of course, yeah, writer has problems, efficiency problems, but I mean, conceptually, it's what it is. And then this is just boilerplate. So the coin flipping I just get from my underlying monad. So if the M is a monad prop, and the delay is simply tel. So the sum just means that, remember the time was fractional, so it's a num, so it has multiplication and addition. So the sum just means that as a monoid for my writer, I use addition. Okay, so that's easy to implement, but it's not enough, because we need this parallelism. Which brings us to my final abstraction, which I call monad rays. And because the idea is you can have 2 computations that can take time and can fail and can be subject to coin flips, and you run them in parallel. And this result looks a bit scary, maybe. So first of all, it's in M. So this whole race takes time, and it can fail. And there's probability involved, so it has undeterministic outcome. But then if something comes out, then it's an either, because 2 things can happen. Either the first computation can finish first, or the second computation can finish first. So we get a left when the first computation finishes first, and a right when the second one finishes first. So in the first case, we get an A, and in the second, a B. And then we get something else, and that is the remaining other computation. So if the first one happens first, we get the A as a result. And then if we want, we could wait for the second one to also finish. So that's this MB. And using this race, we can implement 2 interesting combinators that are very useful in practice. One is first to finish. So if I have 2 things, I simply that have the same return type, I just wait for the first to finish and ignore the other one. And so we can do that for a whole list of things. So we have a list of computations that at some point might return an A. And we just want to wait for the first one. So if it's the empty list, of course, we will never get a result. So it's just absurd. And if it's a non-empty list, then we raise the head of the list against recursively calling first to finish on the tail. And then two things can happen. The head can finish first, in which case we forget this waiting thing, so we just return the head. Or the first to finish of the tail can continue first, in which case we take that and ignore the head computation. And then basically dual to that, there is also something called last to finish. So we have a list of computations and we want to wait for all of them to finish and have all the results, collect all the results. So we have a list of computations, and at some point we will have a list of all the results. And there again in the, not again, in this case it's fine to have the empty list because we just get the empty list of results. And if we have a non-empty list, then we do the same. So we raise the computation of the head against recursively calling last to finish on the tail. And okay, two cases again. So the left case means this head computation returns first, so we get an A. And M is now the remaining computation of this part. So we simply run that, and once we have the result on the tail, we tack on the A. And if the tail part returns first, then we continue the computation of the head part, and once we have the result, we tack it on to the tail. So those two things, first to finish and last to finish, can be expressed in terms of this race. And it's strictly more powerful, the race. So alternatively, in this monad race, then one could use the first to finish and the last to finish as primitives. But then it would be strictly less powerful. But it's mathematically much easier to handle. Actually, this first to finish and the last to finish, one can, on time distributions, one can write down formulas to actually compute that. This race makes things much more complicated, unfortunately. Okay, now coming back to our examples, now we have enough vocabulary to actually implement them. I mean, we don't have implementations for monad race yet, but at least we can express it in monad race. So this case is relatively simple. So I just, I said that all the, I think I forgot the, yes, I forgot that. Right, so the argument D, I forgot to put that on the slide. So the argument D is just, so that is supposed to be on top there. So that's for one edge. So how do we get that? I said it should be uniformly between 1 and 2 seconds and fail with a probability of 10%. So how would I implement that? I flip a coin with p equals 0.9 or 0.1, whatever. And then if I, let's say 0.9, and if it's true, then I do uniform 1 to 2. And if it's false, I throw an error. So that's how I get this one edge. So I'm sorry, I forgot to put that on the slide. And here I just, it's all the same. I said all the edges are the same. Just to make it easier to understand what's happening here, I give them names according to the edges, but it's all the same. So D12 is this part, D24 is that part, D13 is that part, D34 is that part. So if I want to go from 1 to 4, there are two possibilities. I can reach via 2 or I can reach via 3. And I'm interested in which happens first. So I use this first to finish. And so D12 and then D24 is this path, and D13, D34 is that path. And I just use one to finish. And once we add this edge, it gets much more complicated because then it's not possible anymore to use first to finish. Then one really needs this race. So let's try to get through that. So I raise this edge and that edge. So this is this line. So I start in 1 and I do this computation and that computation in parallel. And now there are two cases. The one finishes first, or the other one finishes first. So the first line is the first case. So the signal has reached 2 and this one is still in transit. So what in that case? So either I can reach 4 with this edge, so that's this part, or I must wait until it has reached 3, which can happen in two ways, either when this one that was still in flight finally gets there, or this one gets there. So this is this part, and once it's here, I must still go to 3, so that's that part. And in the second case, if it reaches 3 first and 1 to 2 is still in flight. In that case, there are two possibilities. So I can get from 3 to 4, or I can wait for this one to reach 2 and go to 4. In this case, I can ignore that one because I'm already at 3, so it doesn't help to wait for that one. That doesn't add anything. Right, and so this is that. And now, of course, it would be nice to actually implement it so that we can get a result. And same as before, one can do sampling, which is always good to at least see that it's plausible. I mean, I can write down many type classes, of course, whatever I want, but it's only useful if you can actually implement it. So, and sampling is a relatively easy way to implement it. So the idea is to use, again, a monad M that has randomness, and then just use maybe A comma T. So that means nothing means it fails. That's my monad error case. And if it doesn't fail, it gives just an A, and it takes time T to get there. And let's see. So this is just standard boilerplate stuff. The monad instance is in principle, so if the first one fails, it fails. If the first one doesn't fail, I run the second one, and I apply the continuation to the result of the first. If the second one fails, the whole thing fails. And if the second one also succeeds, then the result of the second one is the result of the whole computation. And the total time, I must add them. So the T is the time the first one took, and the S is the time the second one took. So that's bind. Monad error is simple, it's just nothing. So I throw an error by returning nothing. Probability is the same as before when we didn't talk about time yet, so I used the randomness in the underlying monad, and depending on whether this x that I randomly draw between 0 and 1 is less than p or greater than p, I return true or false. And it doesn't take any time. The delay will always succeed, doesn't return a result, and takes time. That's the point of delay. And finally, the race. So there are a couple of cases. If both branches fail, the whole thing fails. If the second branch fails, then the first one will be first, because the second one never returns. So that means I get a left with the result of the first one, and it takes t as long as the first one takes. And the remaining computation for the other branch, I know it's failing, so it's absurd. Then the mirror image is for the other one. So if the first one fails and the second one gives me a result, it's the other way around. So I return a right. It takes time s, what the second took. Result is b, result of the second. And the rest of the first is absurd because it failed. So actually the interesting case is the just, so both succeed. And in that case, I must now really look which one was faster. So I'm slightly left biased. If I wanted to, I could use a coin flip of 50% to make it fair, but this is not important here. So if the first one is faster than the second one, then the result is a left, and I return the result of the first. And it takes t until the first is there. And now this is the interesting part. So what's the rest of the computation? Well, I have to wait s minus t. I've already waited. T time has already passed, so the remaining time is just s minus t, so that's this. And then that will return the result, the second one. And if the other one is smaller, then it's the other way around. So then it's t minus s. It's a right. I return the b, and it takes s. So that's the sampling part. Okay. And that is actually probably, if you really want to do that in real life, it's probably what you will have to end up doing, because it's relatively fast. So it's almost as, whereas if you try exact results, you have this combinatorial explosion, because there are so many possibilities. And it's also easy to, for example, add this uniform distribution directly. So I now approximated it by splitting interval into many pieces. If you're just interested in sampling, you can use proper uniform distribution and then draw from a uniform distribution in sampling. But of course, at least for small examples, it would also be nice to get exact results, same as we did for our Monty Hall and our dice. So I give a second implementation with exact results, and it's very similar to the list implementation of the standard probability monad. Only now I have triples. So before I had pairs A, comma P, result A with probability P. Now I have triples where the time component is there. So now such a list, component in the list means I will get result A with probability P, and it will take time T. And earlier I said that all the probabilities have to add up to 1. Now they don't, and that's how I take care of the monad error thing. So the difference to 1 is exactly the error case, which makes it nicer because now the type, I mean, there's no unwritten extra law actually. So everything basically of that type is valid. As long as, of course, the sum of probabilities must be less or equal to 1. Right. And again, really what that is a map from A's to basically result A, and this is a distribution of probability distribution of how long it takes. And again, same technical problem, because not every type has an odd instance. We can't turn that into a monad directly, so we first take lists, and then if A happens to have an odd instance, we can convert it. And the implementation is similar to this sampling, actually. So the monad instance, we basically just run the first one, then apply the continuation to the result of the first, and then again, so we must add the times and multiply the probabilities. That's the same as before. The monad error, I already said, just corresponds to the empty list. So we don't have any results. So that's how we throw an error. Probability, also as before, that we just have a list with 2 elements, so true with probability P and false with probability 1 minus P, and both are there instantaneously, so don't take any time. Delay is also simple, so no result, probability 1, and it takes time because it's a delay. And of course, the interesting one is the race, and that is actually similar cases now to what we had in the sampling. So there are these cases that both fail, that one fails, the other fails, or both succeed. So we first compute this weight. So weight is the probability that we will get some result. So it's the sum over all p's in the list, which can be less than 1. So this fx and fy is the complement of the weight. This min-max is just to normalize it in 1. So in case you use double probabilities with rounding errors, I just want to make sure that I'm always between 0 and 1. So morally, you can ignore that. And so these two are now the case where the other one fails. So this first line handles the cases where the second computation fails. So I just return the first one. So that corresponds, remember, maybe we should go back to here. So this is now this case. The first one succeeds, the second fails. And this now looks, if we do it here, looks like this. So it's just the time to wait for the first one, probability of the first one, but I must multiply it with the probability that the second fails. That's this Fy. Same here for the other one. The interesting case is that both succeed. So then it's very similar to the sampling. So I check how long the first takes, the second takes, and then I compare the times. So if the first one is faster, again, I'm left biased and I don't care. So then the first one wins, so I return a left, it takes TA, multiply the probabilities, return that result, and the remaining computation is the B, and the remaining time is just the difference between the times. And same in the other case. And then I must just combine all these 3 cases to one list. Okay, and that we can now apply to our problem, to our original problem with these graphs. And this is what we get. So this is now an exact result, of course, modulo this fact that we don't have a proper uniform distribution, but just one split into 20 cases. But the probability is correct, because that doesn't matter, and probably the mean time will also be correct, and also the min and max. So if you think so, the min and max should be between 2 and 4, because the fastest possibility is that it succeeds and takes 1 second for each hop, because it was uniformly between 1 and 2. And of course, the slowest that can happen is that it takes 2 seconds for each hop, so that's 4. And this time it's, I mean, it has this weird shape because we have this parallelism in, so that makes weird things. Okay, and so the probability is 96% that it will actually get from 1 to 4. So because remember, each hop has a probability of 10 to fail, but we have now 2 possibilities, so that's somewhat complicated. And if we add this extra edge here between 2 and 3, it changes, I mean, only very slightly, but it does change. So it was 96%, now it's 97%. And we see that now suddenly it's possible to take up to 6 seconds, which happens if it takes 2 here, then has to go down to here, and then 2 there. So that's the 6-second path. The rest from 2 to 4 is very similar to before. So it looks very different, but I think mostly because this tail here, this is now the effect of the additional edge. Yes?
Does that mean the area under the curve integrates to 0.97 here and not 1?
Exactly. Exactly. So that's exactly the point that, I mean, normal probability distributions always integrate to 1. And because we allow failure, it can be less than 1. Yes. Right, and yeah, so you can do things like that. I mean, unfortunately, I think in practice it's not, I mean, this already takes 5 seconds or so to compute. And if you make it much bigger, if you make it to realistic dimensions of a real-world network, I think that's infeasible. But I still feel it's valuable, because if you have whatever system where you use whatever optimization or sampling or whatever, at least you now have exact results that you can compare whatever you do with, and then you can, like, it's like a sanity check to see whether whatever you do makes sense. Right, and that's the end of my talk. Thank you very much.
Fantastic. A question at the back here.
Yeah, thanks for your talk. You mentioned a few times there about how you'd have to change it in order to accommodate continuous delays or real uniform distributions of delays. Presumably, like, continuous PDFs would have the same kind of considerations, right? Because you've got discrete events there. But if you had a PDF over a continuous variable, would that essentially be the same thing as in the implementation as a continuous delay function?
Yes, I mean, in practice, of course, we would rather have continuous ones. And I mentioned that you could also not do this race and instead the first to finish, last to finish. And if you do that, then you can actually do more interesting delays. Then you can do piecewise polynomial delays. So because it turns out that under convolution, which is this adding of delays, and also the first to finish and the last to finish operators, if you have 2 distributions where each piece is given by a polynomial, then if you combine them with convolution or first to finish or last to finish, you again get something polynomial. So that was for a long time my hope that one could do that actually. And, but it turns out with this race it gets complicated. I mean, I don't know how to do that. I think it should be possible. I think the result will again be a piecewise polynomial, but it's somehow very messy to actually figure out what to do with the polynomials. But yes, so with these continuous things, one can use any PDF in principle. So it must be closed under the operations you want. So you want to combine delays sequentially, so which in the language of distributions corresponds to convolution. So whatever class of PDFs you consider must be closed under convolution, and it should also be closed under this first to finish and last to finish. And as I said, piecewise polynomials are one possible class that one could take. There are other options like, I think, exponential distributions, but they seem to be less useful in practice because we would like to have uniform. The nice thing about this piecewise polynomials is that uniform distribution is piecewise polynomial. Yes?
I have a more theoretical question.
Yes?
Okay, thank you.
yeah, it seems to me that what you try to achieve with your own library is also doable with existing probabilistic programming languages like Anglican, which is based on closure. So my question is it possible to extend your library into a more general probabilistic programming library or framework?
You also have managed base in Haskell.
Oh yeah, cool.
Probably. I mean, I'm not sure I want to do that. It was more my personal curiosity.
Right.
It was not so much about actually doing that in a performant way. I just wanted to understand what kind of abstraction you need to express these things. So it was more about coming up with this monad rays abstraction, which I sort of like quite a lot because it's so nice symmetrical, and I don't know whether man hopefully could turn it into something practical. But for me, I mean, the motivation was more to understand conceptually what is added, what extra minimal set of operations you need in order to model stuff like that.
Right. I have another question related to race, because it seems to me your abstraction looks similar to races where people use in the concurrency effects libraries. Like, did you study some other libraries to get inspiration or ideas?
I mean, I think in async there's a race where you can really raise two threads, of course, and that's where I got the name from. But
right, is there like commonly shared concepts, like more mathematical or?
I don't know.
Okay,
Sorry.
Yeah, I'm just curious about it. Okay, thank you.
Okay, I think that's us. Well, big round of applause for Lars. Fantastic stuff. Thank you.